Section 12.3 is going to continue with two more types of solids. We're going to actually spend 2 days on this one as well. We're going to talk about just pyramids today, and then we'll talk about another shape tomorrow, okay? Now, this is going to talk about just surface area pyramids. We'll eventually get to the volume stuff eventually. Now, a pyramid, I know you guys know what a pyramid is, okay? So kind of some great examples is, like when you think of a pyramid.
Oh, I think back to Egypt and think about all the pyramids and
the great pyramids.
Yes.
Now, that's a specific type of pyramid. We're going to see other types of pyramids. A pyramid is a polyhedron. So, what is another type of polyhedron that we've spent some time on already?
Well, we've talked about prisms.
Prisms. So, are prisms and pyramids the same? No, because if you read the definition, it says in which the base, so notice it just has one base this time. And hopefully you kind of get a visual of that anyway. With a pyramid, it has one base, and it is a polygon, so that's why it's a polyhedron. And all its lateral faces are triangles. Okay, so
Before, when it was regular, they were all rectangles, so now they're all triangles. Okay.
Yes, with a prism, all the lateral faces were either parallelograms, but yes.
Well, we just focused on the regular ones. So
now they all come to a common vertex. So if you can kind of get a visual of it, we're going to have a sketch of it in just a minute. But you have your polygon base. And that polygon, there's no restriction on it, as long as it's a polygon. So could it be a triangle base?
Sure.
Yes. Could it be a quadrilateral base? Yes. Could it be pentagonal? Yes. And then all the lateral faces. So the rest of the stuff are triangles. Okay. Notice, just like a prism, a pyramid is going to be named after the shape of the base. So if it's a triangle base, it's going to be a triangular pyramid. Okay.
Okay.
Some vocab that we've seen before: a lateral edge. Okay, a lateral edge are the intersection of two lateral faces. So an edge is remember a segment. Okay, just a reminder there. So where your two lateral faces, now what are lateral faces again?
They're the ones that are kind of wrapping around the base, around the sides.
But in a pyramid, what are they?
The triangles.
Triangles. So when you have two triangles that intersect, they form a lateral edge. And the reason why we need to kind of understand that is because when we start using some of this when we find the surface area. Now, a base edge, on the other hand, is the intersection of the base and the lateral face. So you have the base and the lateral face that intersect. To me, a base edge is basically the sides of the base. Okay?
Right.
So a lot of times that's what I think of it. It's the sides. What I mean by sides are the segments of the base. All right? So if the base is a quadrilateral, there are going to be 4 base edges. Okay? Now, altitude or height, we've seen this before, it's still that perpendicular distance between the base and the vertex. So here's the difference. When we talked about cylinders and prisms, you had the perpendicular distance between the two bases. Well, we only have one base. So if we have our vertex, a vertex is a point. Okay, so if you draw the perpendicular segment to the base from that vertex point, then that's your height or altitude. Okay? So we're going to see some more vocab and then kind of do some surface area with it.
All right. So regular. We've talked about this idea of a regular prism before.
No, right prisms.
Oh, that's true. We did. Sorry. A right prism before. A regular means that it is what? What are the 2 requirements?
Congruent sides and congruent angles in the figure.
Congruent sides and congruent angles within the figure. I like that you said that, because here's the thing. When we're talking about a regular pyramid, we want to talk about a pyramid that has a regular polygon for a base.
So that limits it right away. So the base, if it has 4 sides, then that base would be a square, which is the most common pyramid.
Right. So what are some other regular pyramids you could think of? What are some other regular bases?
Regular bases, equilateral triangle. And then after that, it's just like, okay, if it has 5 sides, it'd be a regular pentagon, a regular octagon. But we know how to find stuff about regular polygons from chapter
We spent
11.
a whole chapter focusing on a lot of that. So when you have a regular pyramid, I just want to emphasize that that's kind of what we're going to focus on the most.
Okay.
Because that's where we can get more specific.
Yeah.
All right. What do you think is true if if the base is a regular polygon? What do you think is going to be true about the lateral faces?
Well, they're not going to necessarily have to be regular, are they?
Not necessarily.
But if you read onto the definition, this is kind of, because you can't really make this assumption yet. Notice that the height meets the base at its center. So the fact that kind of the height or that center is directly above or below that vertex, that's going to force all of the lateral edges to be the same. Okay?
Right. Now, is that necessarily true for just every base that is a regular polygon, though?
As long as it's a regular pyramid based on that definition.
Right. Okay. So here's the idea. If you see a regular pyramid, the regular polygon by itself does not necessarily mean anything. But to be a regular pyramid, it has to have a regular polygon base and its height meets the base at its center. Okay. So that's the two things that we want to stress. Because if I have just a regular polygon for the base, but I have a point out here where all those vertices are meeting, it's not regular.
Exactly.
So to be regular, it has to have two requirements.
And guys, most pyramids that you deal with on a regular basis are regular.
Yeah.
Okay. But I want to stress again what you were kind of commenting about the lateral faces. So because that vertex is directly basically above that center, all those lateral edges are going to all be congruent to each other.
Right.
Okay. Now, are the lateral edges going to be congruent to the base edges? Not necessarily.
Yeah.
All right. More than likely not. So, a kind of a little side note, if you can write this for us, Ms. Hogravy, on where regular pyramid, the lateral faces basically are isosceles triangles.
Yeah. And that is only true if it is a regular pyramid. But that's what we're going to focus on the most.
And if you kind of get a visual of that, like the isosceles triangle, it's formed by the two lateral edges and then your base edge, if you think about that.
Yeah. So those are just some things to emphasize, just some things to be aware of. To be regular, it has to have two criteria. Regular polygon for the base, so we know that all these sides are going to be congruent.
So the base edges are congruent.
Base edges are congruent, not necessarily to the lateral edges. Pardon me. And we know that all the angles are all going to be congruent, which if it's a quadrilateral,
in this case, they'll be all right angles.
They're all going to be right angles. Okay. Slant height. New word. We haven't really focused on slant. I shouldn't say totally new word, but we haven't focused on it very much yet. Slant height is going to be the altitude, because it's a height, of any lateral face. Now, what people commonly want to think that this is it's a lateral edge, but it's not.
So if you, but why don't you draw? Will you draw a lateral face for me?
And what did we say about the lateral face?
It's an isosceles triangle.
Absolutely.
So let's label the lateral edges the same. Okay, and again, those are the lateral edges. That's your base edge. Okay. If you draw in the height of that, that is your slant height.
And we typically use an L for slant height. So just something to be aware of. So when I'm drawing it on this picture, I'm going to draw the slant height just for this side right here. It's going to come right down the middle of that figure if it's a regular pyramid, because this is an isosceles triangle. All right, now I want you to notice that the slant height that's here is also, it's perpendicular to the base edge, but also if I connected that with the, and kind of drew in this little segment that connects from the actual height.
And here's the thing. Notice that the slant height and the height are not the same thing, guys.
They're not the same thing.
The height is the perpendicular distance between the vertex and the base. The slant height is only perpendicular to the base edge.
Right.
Okay, from the vertex.
If I drew in that little triangle that exists, though, between the actual height and the slant height, first of all, notice that the slant height would be the hypotenuse of that triangle, so it's longer than the actual height. But also, what measure do we call it when we go from the center of a circle and we
center of
a circle, center of a figure, of a polygon.
Regular polygon.
And we bring it down to join where that kind of, that's, because we know this is isosceles triangle, the center of that
base edge.
Base edge. What do we call that measure?
Well, I'm thinking regular polygon. If I go from the center of it to the actual side of that polygon, that's what we call the apothem.
Right. So one thing I want you guys to realize is that also, if you connect the height with the slant height and the apothem, it also forms another right triangle. There's lots of right triangles you're going to notice in what we're going to be doing today. So just something to be aware of. We're going to see the slant height is going to be the perpendicular height, the perpendicular distance from that vertex to the base edge of one of the sides. And it's the same, if it's regular, it's true for any of the sides. There's a little right triangle we can see there. There's another right triangle that we can see when we talk about the height with the slant height and the apothem. So just some things to be aware of because we're going to see this stuff coming up a lot.
Okay, now that last slide, guys, that's something you just, again, kind of have a visual. Drawing a pyramid, I'm going to go back here. You may not want to draw the whole entire pyramid. You might want to draw like maybe the right triangle formed by these things, or draw the lateral face. Again, this is a lateral face, okay? So just stressing that. Now, we're going to get to, whole goal is to get to surface area, all right? Now, we know so far what we've done is taken the three-dimensional solid and flatten it into a net, taking it two-dimensional, because that's what really area is, two-dimensional, right? So let's say, and this is just a special case, let's say we have a regular hexagonal pyramid. And why do I call this a regular hexagonal pyramid? Well, because the base is a hexagon. And why did I say regular? Well, because the base is regular. Guys, if I didn't tell you it was regular, this formula we're about to explore won't work, okay?
And because it's regular, all those lateral faces are all congruent.
Exactly. So just a little side note, okay? Again, if it's not regular, you're going to have to find the area of all of the faces individually. But because it's regular, we know this is a regular base, and we know these are all congruent triangles, but they're all congruent isosceles. Remember, because the lateral edges all the lateral edges are going to be congruent, okay? Yes. Now, let's get a game plan. To find the surface area, and I use capital S, we're going to have to find the area of what?
Well, definitely one base.
And only one base, so not two capital B. So we're going to use capital B for the area of one base. And then we're going to add it to basically all of this stuff. What do we call this stuff again?
The lateral edge, lateral faces.
So we kind of talked about the lateral area as the capital L, right? Now, area of the base will all depend on what kind of base it is. If it's a square, well, it's just side squared.
Right.
If it's an equilateral triangle, we can use the 1/4 side squared radical 3. But if it has more than 4 sides, we're probably going to use 1/2 the apothem times perimeter.
Right.
Okay. So this is going to be varying on the type of polygon that we have is for the base. Here's the deal. The lateral area is formed from all the different triangles that we have. Okay.
Right.
Now, we already said all of these triangles are the same. So if I could find the area of one, then I could find the area of all of them, right?
Right.
Now, I'm going to draw in. Now, how do we find the area of a triangle?
1/2 base times height.
Now, I'm going to draw in its height. Now, the height of this triangle, lateral face, is it the same as the height of the pyramid?
No, it's actually the slant height.
Yes. So I'm going to make a little note. This is my slant height. Now, you said 1/2 base times height. What would the base be of this triangle? Think about it in relationship to the pyramid.
Okay, well, I know that it's just one of the base edges.
And so sometimes we call it, it's just a side of the base.
Right.
So I'll just call it S for side length of the base. And like you said, it is a base edge.
Right.
You're exactly right. Okay, so we know surface area is your capital B, base area, plus you said 1/2 base times height. And I'm using the S times the slant height.
Right.
Okay. Now, that's only one of the triangles.
Yeah, now we've got 6 of them.
Now, is there always going to be 6 of them?
No, let's say N for number of sides.
So we're going to take this basically times the number of sides. All right. Again, I like that you said in this case there's 6 of them, but if it was a regular octagon, we'd be multiplying by 8.
Right.
Now, I'm going to do kind of a little switch around here. All right. If I have, so my surface area equals capital B plus 1/2, I'm going to flip-flop these things because multiplication, it doesn't matter. So S times N times L. All right?
Okay.
So I'm going to focus on just this piece right here. When you take the side length of that base, so that hexagon base,
right,
and multiply by the number of sides, what are you finding?
That's the perimeter.
The perimeter. So capital B, so area of the base, plus 1/2. So instead of this, we're going to have capital P times the slant height. This, guys, is the formula for surface area of a pyramid. Regular pyramid.
Yeah.
Yes. Okay, so just to kind of, we just showed you how this came about, right? So if you look on the next slide, all right, it has it there for you. Make sure, if you don't have to write it down again, unless you want to, make sure you communicate what that is, All right, again, what's the capital B stand for?
Capital B is the area of the base.
So the base area. And what's the capital P?
Perimeter.
Perimeter of what?
Of the base. That's good to make sure that we know.
And then what's the slant height?
The slant height is the height of the lateral face. So the height of the triangle face.
Okay, I'm going to make a note. It's the cursive L is the slant height, and this is the height of the lateral face. Now, and that lateral face is going to be an isosceles triangle.
Yeah.
Okay, remember that. Isosceles triangle. All right, so all of the little pieces. Notice this formula is different than the two that we learned with cylinders and prisms because it doesn't have two bases, that's one. And notice it doesn't have the height involved. It has the slant height. So if I give you the height of the regular pyramid,
it's probably to help you find.
We're probably going to be doing something with that. Okay? So let's practice this. Let's do some examples.
I think that sounds like a great idea. Okay. So when you're coming up to a problem like this, and you notice that you're finding the surface area of a regular pyramid, the very first thing you probably want to think is what?
Let's write down the formula.
I think that sounds great. So surface area equals?
Capital B plus 1/2 perimeter times the slant height.
Love it. Now, looking at this picture, do we have the area of the base right now?
No.
But what kind of a base is it?
Well, here's the deal. The picture, to me, it's kind of hard to kind of tell that it's regular, but it does say it's regular. Right. And so I look at the base, and I see that it's a four-sided base, so that means it has to be a square.
It has to be a square because if it's a regular quadrilateral, it has to have four congruent sides. So we know it's a square base. How do we find the area of a base of a square?
Just side squared, so 10 squared.
And if you said 10 times 10, same thing, which is going to give us?
100.
All right, so we know the area of the base. Do we know the perimeter of the base yet?
No, but we could find it, same deal. So since it's a square, you're just going to take 4 times the side length of 10 and get 40.
Love it. Okay. Those weren't too bad, especially when it's a square. It's nice and easy. Slant height. Do they give us the slant height?
They give us the height, so no, they actually don't. But they do have it drawn in there for us.
They did draw it in. So I'm going to go ahead and make the little triangle that connects that. And the right triangle.
And what she drew in, that dotted guys, dashed or whatever, that's the apothem.
Right.
And that's the apothem of the base.
The apothem of the base, exactly. Now, let's talk for a minute because with a square, the apothem is kind of a special thing in a square.
Yeah.
What do you know about this apothem of a square?
Well, can you draw out a square just so we can kind of get a visual of this?
I think that's
because I know where you're going with it, but not everyone can remember
this.
That
necessarily.
So if I know the side length is 10, now I know the apothem's going to split that side into half, so those are going to be 5 and 5. Draw in the radius of that.
Yep.
And I know that the central angle is going to be 90 and cut that in half. That's a 45, 45, 90.
The whole thing is 90, so this one is 45. So we have a special right triangle.
So that means the apothem is just going to be 5.
Right. It's the same as the half of the base because we have a 45, 45, 90, so this is isosceles.
Now, is that going to be the case in every regular base that the apothem is half the side length?
Definitely not.
No.
It only works for squares,
exactly.
actually, because they're the ones that give you the 45, 45, 90s. All right. Now, right now I have that the height is 12. The apothem was 5. We needed the slant height.
So I'm thinking use the Pythagorean theorem.
Yeah, because this is a right triangle. All right. And we're trying to find the C. So let's go ahead and say
L squared equals 12 squared plus 5 squared. So that's going to be L squared is equal to 169. Oh, I was just going ahead.
Go ahead. No, that's fine.
Yeah. And then L is going to be 13. So that's the slant height.
All right. So now we have all of our parts. Can we go ahead and put these into the formula and then solve? Sounds good. So the surface area is going to equal, we said the area of our base was
100
plus, oh, it's frozen. Okay, 1/2.
The perimeter, it's just 40. It's sticking on you.
It is definitely sticking on me. 40 times our slant height, which was
13.
All right.
So if I just kind of simplify that down, surface area is equal to 100. Half of 40 is 20. 20 times 13 is 260. And then so the surface area total is 360 square centimeters. Now, guys, while she's finishing it up, I want a word of advice. Don't feel like you have to draw the whole entire pyramid.
No.
Draw just the base. Because remember, the base area and perimeter of the base all involve the base. And we even had to kind of use the apothem to find the slant height in this. So drawing just the base could be a good visual for you.
Yeah,
okay?
Definitely.
All right. So it says find the surface area of the regular pyramid. Same exact direction. So first thing we should do is...
Let's write the formula.
All right.
So surface area equals the area of the base plus 1/2 perimeter slant height.
Okay. So here's the deal. Yes, I have a picture here. Okay, kind of helped you out here. Let's just go ahead and draw just the base because there's a lot of kind of edges in here, kind of hard to kind of see what's going on. So I'm just going to draw the base. And again, you don't even have, we'll even talk about, do I even need the whole base? Well, not necessarily, but hexagon's not too hard to draw, okay? Kind of gave away what my question was next. So it's a regular hexagonal. Yes, yeah. Okay. Hexagonal. So I have a base edge. Notice the base edge is 4. What's this 9 represent?
The 9 is the height.
Is that the same thing as a slant height?
Not the same thing as slant height.
And remember, slant height should be larger than the actual height of the pyramid. So keep that in mind. All right, so we need to find the base area, which involves, of course, the hexagon. The perimeter base, again, involving the hexagon. The slant height, which has some things involving the hexagon as well. Which piece would you want to start with?
Let's start with the base stuff. So let's do area of the base and perimeter of the base. And we need perimeter to even find area in this case. So it's going to kind of
come into play. Perimeter of the base is usually the easiest to find. If you know the base edge, let's just knock that out. Okay, so perimeter of the base, you're going to take
4 times the 6 sides.
So all right, so we got this piece already.
Okay.
All right, now to find the area of the base, how do I do that?
Well, since this is a hexagon and I've already got the perimeter, let's do half apothem perimeter.
Okay, I like this idea. I'm going to jot this down as a reminder. We already have the perimeter, so we're going to put that in. We just need to find the apothem. And even better, guys, you're going to find out that we need the apothem to find the slant height.
Yeah.
So this piece that we're about to find is going to help us find the slant height as well. All right? Okay. So what does the apothem do again?
The apothem splits the base into 2 congruent parts, so those are each 2. And when I draw in the radius, if the whole central angle of a hexagon is 60, so that little angle up at the top there is going to be 30. So this is a 30, 60, 90 triangle.
Love it, which is nice.
It is great.
Special right triangle.
So when the shorter leg is 2, which is what we're given across from the 30, the longer leg is going to be a 2 radical 3.
Which is what we want. That's the apothem.
That's the apothem. We don't need a radius, so silly to even...
All right.
It's 4, but
so I have the perimeter. Now we have the apothem. Let's find the base area. So 1/2 the apothem, which is 2 radical 3, times that perimeter of 24. So let's leave it in radical form.
Okay.
A couple of reasons why I see that is I see no units. All right. So 1/2 of 2, that's so it's
just 1 radical 3. So times 24, so 24 radical 3.
All right, so now I've got these 2 pieces.
So now we need the slant height.
Okay.
And the slant height, I remember we were talking about when we draw in that slant height, which it's not drawn on the normal, on the picture that we have here. But when we draw it in, we know that it is the height of one of the faces, and that with the apothem and the actual height, it forms a right triangle.
So let me draw this in. So basically, you said again, this is your height.
That's the actual height.
Which is your 9. This is your slant height, which is what we're trying to find. And this is the apothem, which is?
Our 2 radical 3.
Okay. So what are we going to have to use to find that slant height?
Pythagorean theorem.
Okay. So I'm finding the hypotenuse.
So L squared is equal to our 9 squared plus 2 radical 3 squared.
And when I do that, I have to square the whole thing.
Yes. And again, guys, make sure you're squaring each part. Don't leave it off.
Okay.
So 9 squared is going to give us the 81. And 2 radical 3 squared would be like a 4 times a radical 9, which is 3. And 4 times 3 is going to give us 12. So 81 plus 12 is going to give us a 93. And that's not going to be as pretty. We're going to leave it as just radical 93 to be exact.
Okay. So do I have all the pieces to find the surface area?
We do.
I do. So let's go ahead and substitute those numbers in. So I'm going to have surface area is the base area.
Which was the 24 radical 3.
Plus 1/2 the perimeter, which is...
The perimeter was our 24.
times
radical 93.
All right, let's see if we can. I see we can simplify down here, can't you?
Yeah, we can at least multiply those two numbers. So 24 radical 3 plus 12 radical 93.
Now, can I combine these?
I can't, and radical 93 doesn't simplify any further, so that would be my exact answer.
This would be the exact answer, okay? And of course, if it has units, which I'm guessing a lot of times these will, then you can type this in your calculator, and what do you get approximately?
Approximately 157.29.
Okay, so just something to keep in mind. So again, guys, notice how I redrew, and again, remember what I was talking about, you don't need to draw the whole regular base. If you want to just draw that little right triangle in that regular base, but keep in mind, this right triangle is different than this right triangle.
Yes.
This right triangle is on the base, this triangle is within inside that pyramid. Okay,
Right.
so just some differences, a lot of right triangle stuff. All right.
Imagine that. We're
I
still
know.
using triangles. They just don't go away in this class, do they?
I know.
All right. Last example that we want to take a look at with you. We have a regular pentagonal pyramid, which pentagon is going to be the
base.
base. So I'm going to go ahead and draw in a pentagon. It's a regular pentagon.
Especially, here's the deal. Would you draw the whole pyramid?
No, I don't want to draw the whole pyramid.
So I love that she's just drawing the pentagon base.
Okay. And it has a base with side lengths of 18 inches. So each side is going to be 18 inches.
Since it's regular.
Since it's regular, because that's what they tell me. The slant height, I'm just going to write that off to the side for right now. L is 24. That's kind of nice that they gave it to us, because usually in the formula, that so far that's been the piece that we've had to find also in order, along with the area of the base. So that's helpful. Find the surface area of the pyramid. All right, so the first thing we're probably going to do is write down
the formula.
So surface area equals
the area of the base plus 1/2 the perimeter of the base times the slant height. And they already give you the slant height. So all we're focusing on is that pentagon.
Yeah, the base. We need the area of the base and the perimeter of the base. Which one probably would be easiest to find for this one?
Perimeter of the base.
Okay.
So 18 times 5, which gets you 90. And we're going to need that to find the base area anyway. So
Exactly, because to find the base area, I know I'm going to have to do what? For a pentagon.
The 1/2 the apothem times perimeter.
Yeah. And guys, notice how I'm rewriting these formulas each time? It's really a good practice to do that. Just write down the formula and then put in the pieces that you know. We already know the perimeter. We need to know the apothem. So let's draw in the little right triangle. And let's talk about this one, because pentagons, they're not quite as lovely of figures.
No.
What do you know about the central angle of a whole pentagon?
Well, we know that the apothem bisects that side. So
okay,
that's
so let's
9.
do our 9s first. Sounds good.
Okay, so in that like blue right triangle, we only have really that it's a right triangle with one side. So we're going to have to find that central angle like you're telling me to do. So 360 divided by 5, that gets you 72, and then cut that in half, and I get 36.
It's not a special right triangle.
So you're going to have to use trig.
We're going to have to use trig. What if I'm trying to find the apothem?
I'm going to use the tangent ratio
Yeah. So let's take the tangent
of 36
equals.
equals 9 over a.
And when we go ahead and cross multiply, you'd end up with a. The apothem is going to equal 9 divided by tangent of 36.
Which that makes it about 12.3874.
Now, I'm going to leave that big, or Thomas Palermo at least, to leave for that big long decimal in that calculator. Because we could go ahead and find the base area using this exact value, right? So we know the base area is equal to half of that apothem times the perimeter. And the perimeter was 90. So what are you going to get? What are you going to get when you take this big long decimal times 90 times 0.5? Approximately.
About 557.4347.
Okay. And again, we're going to leave the big long decimal in our calculator, because we know the surface area, we already had all the other parts, is going to be that 557.4347 plus 1/2. We said the perimeter was
90.
And the slant height they gave us as
24.
24. And what do we get when we type all that stuff into our calculator? Surface area approximately will equal.
Hold on one second.
That's all right.
1,637.43
Love it. And
inches squared.
yep, they gave us a label, so inches squared.